Hey guys, so we're going to start talking about light, and this is kind of a big topic, so I've broken it into a couple of pieces. Today, what we want to focus on is what light is. So, what is light? Okay, light is a form of energy. Okay, now it is a unique form of energy, unlike all the other types of energy in the universe. It's very unique in the universe, actually. To describe it, it takes two separate models, like there's two ways to think of it. We're going to get to this in more detail in the second part of this, but you can think of light as both a wave and as a particle. Okay, now if we're talking about light as a wave, we call it electromagnetic radiation. And if we think about light as a particle, we call it photons. In reality, light is neither a wave or a particle. It's both a wave and a particle at the same time. And I know those are contradictory, but it is. It has properties of both. Okay, so before we get into that whole confusing idea, let's just talk about light in general. So, first off, white light. White light is all the colors mixed together. So, if you take white light and you shine it through a prism, you will actually get the whole spectrum of colors: red, orange, yellow, green, blue, and violet. And you'll be able to actually see them there. So, white light, whenever you shine white light on something, you're actually shining all colors, all possible colors, the entire spectrum on something. Now, that white light is going to interact with an object. How it interacts depends on its properties. So, when light hits an object, it is either going to be absorbed, or it's going to be reflected, or it's going to be transmitted. Transmitted means it goes right through. So, things like glass transmit light, it goes right through it. It depends on the properties, like what material it's made out of and how its atoms are going to interact with it, which is why this is relevant to chemistry, because we're going to talk about how atoms interact with the light. Now, there's a fourth thing that light can actually do, and that is light can be emitted by atoms. So if you give them energy some other way, through electricity or heat, or through some high energy light, it can actually re-emit that light, and basically they'll glow. Okay, but that's a fourth way, which we're going to get into even later. So reflected bounces off, absorbed, it actually gets absorbed, that energy is absorbed by it, or it just goes right through, it's transmitted. Okay, so let's talk about absorbing. Okay, objects will absorb some colors of light, and then they'll reflect other colors. So one object might do both. For example, a red apple, white light hits it, all the colors hit the red apple. It absorbs violet, blue, green, yellow, orange. It absorbs all of those colors, but the one color it doesn't absorb is red. Red is reflected, and then that's what actually hits our eye, and so that's what we see. So the thing that we see is what is not absorbed by the object. Now, some of that absorbed light, all those colors that are absorbed, gets turned into thermal energy. Okay, so when it absorbs things, it gets more energy because it's absorbing the light energy, so things will actually get hotter. They'll get warmer when they absorb the light. If something is black, it absorbs all visible light. Right? So all color is absorbed by black surfaces, all things that we can see, which is why we perceive it as black. Same thing as darkness, if you will. Darkness is the absence of light. So black is that same color. There is no light being reflected by it. We just see an absence of light there. So white, anything that's white, what's happening is it's reflecting all colors. Okay, all visible color is being reflected there. And if you see an actual color there, that means it's absorbing some colors but not others. It might just absorb one or two, and then it's kind of slightly different shade of white, or something like that, or it absorbs a lot, and so you get a very distinct color there. Now, the more color it absorbs, the more energy it's going to get, and so the hotter it's actually going to be. So a white surface, which reflects all colors, is actually not going to absorb as much energy, and so it's not going to get nearly as hot as, say, something that is black. Right? So how does a mirror work? Well, white light, if something is white, light shines on it and it reflects that light out, but it doesn't reflect it out in the same direction it came in. A mirror, on the other hand, does. Okay, it's perfectly smooth, and so it reflects it at exactly the same angle at which the light hits it. So what this means, if light hits a white piece of paper, it will reflect that light, but it kind of goes in all sorts of directions, so you don't see anything except the color white, which is the white light. Whereas the mirror, since it reflects off at a perfect angle, what you see is the light that hit the object in the first place, exactly as it hit the object, so it's a perfect image that you see in the mirror of what light was hitting it. So this is a little creepy to think about, but because it's basically reflecting that exact image and not reflecting the light there, absorbing anything, a mirror is a surface that you've never actually seen because you only see what light hits it and gets reflected off of it. So images in mirrors are another image of something else. You've never actually seen the surface of a mirror. So what can a human see? Well, humans are limited by their eyes. Right now, in your eye, you have what's called cones and rods, and these are receptors that pick up light. The cones are the ones that determine color, and you have 3 types of cones. So humans can actually only see 3 colors, 3 receptors for those 3 colors. Red, green, and blue are cone receptors. So those are the colors we can perceive. Now, if something that's in between those colors, like yellow, hits our eyes, what happens is it actually stimulates both receptors. So a yellow light will stimulate the green and the red at the same time, and our brains can interpret that as knowing that that's the color yellow. So we can see all the colors that are in between as well, depending on which of those receptors are being stimulated and combinations of those receptors. This makes it interesting because we can actually trick our brains into thinking we're seeing a color even though we're not. For example, right now you guys are seeing this on a computer monitor. There is no yellow on your computer monitor. Your computer monitor has red, green, and blue lights, very tiny little pixels, and it is combining red and green in specific ways to give you the idea of yellow. So anytime you're seeing yellow on your computer, what you're actually seeing is red and green, and your brain is interpreting it as yellow. So there isn't actually any yellow light coming off of your computer screen, which is kind of weird to think about. The rods, by the way, help determine intensity. Okay, so they kind of tell you how bright or dark something is. If it's too dark, your cones can't pick up anything, and so you will only see in black and white. This is why, like, in a dark room, it's really hard to tell colors, but you can still kind of see outlines of things and kind of see what's going on. It's really hard to see what color it is. It's because our rods are doing most of the work there. We can't see color. So we are very limited in what we can see. This is essentially the entire light spectrum. We have radio, microwave, infrared, then we have the visible light. This is what humans can see, and it's a very, very small portion of the entire light spectrum. We also have ultraviolet, X-ray, gamma rays, which are dangerous. We hopefully don't want to be seeing those, but humans are very limited here in what we can see. Other animals, though, do have the ability to see different parts of the spectrum. For example, snakes can see some infrared, birds and insects can see some ultraviolet. So if you take a look here, this is sort of what a human sees, and we've got our 3 types of cones here, the red, the green, and the blue that we can kind of see and mix things with. So this is what we can see. But a bird will actually have a 4th one right here, where they got a slightly different cone in the middle. It's not quite green, it's more like cyan, but they have a 4th cone right there, which allows them to see ultraviolet, and so they actually have a wider range here. They can't quite see as red as we, but they do have a wider range. And so when you look at a flower, we can basically see certain colors there, but they will actually see slightly different colors because they can see that ultraviolet. And so there's some colors in that flower that are ultraviolet that we're not perceiving. So flowers can be pretty cool in the ultraviolet. Here are some videos which kind of try to show you spectrums that we can't see, like infrared and ultraviolet.
What thermal imagery allows you to do is to actually see those, and this is actually quite useful for finding people because people generate lots of heat. You certainly see that my nose is colder than the rest of my face. Actually, now you see it better. You see that my hands are colder than my arms. So there's one of these interesting things. If you want to hide from, say, the visible part of the spectrum, I can get a black bin liner. And what you'll find is this actually is very good at hiding me from the visible spectrum, right? Blocks out all of the light. However, this is polythene, and what you'll find is for the infrared, it's not quite so good at actually hiding my body heat. That is, the infrared will go through this black plastic, but visible light won't. And likewise, you can get things at the other end. So here's another plastic called Perspex. So all I've done is I've swapped to a different representation of heat on these things. So again, you can see that the Perspex here is absolutely fantastic at screening out my body heat. So this will be great for hiding from infrared, not so good for the visible, but what you'll find is that it does actually get warm where I've held it, you see. So where my hands have been holding it, you can see the fingerprints. And of course, other things that you're just a nice thin piece of paper, absolutely fantastic for hiding from the infrared. But you have to make sure, because you can see heat, if I touch the back of this paper, what you can see is very quickly it actually adopts the temperature of my hand. So even though you can't see where my hand's been on this piece of paper in the visible, in the infrared, especially if I push it hard or a little harder, see the handprint.